So let's talk about what is a kernel. The kernel is the heart of a device. Whenever a device boots, the BIOS gives the control to the kernel and then the kernel loads everything up in your device. You can even see your kernel version in the About Phone settings in your Android device. So the kernel is a part of the operating system, a part which controls all the low-level managements. The CPU scheduling, memory allocation, and the interrupts we've been studying, where do these occur? That's right, inside the kernel. The kernel is responsible for making the device you're using fast and optimized, along with helping with its security functions. Let's learn about how in the next section. What does the kernel do? So when we open up, for example, a Chrome window, who's to say the Chrome window won't just take up all your RAM's memory for itself? The kernel. See, the kernel acts as a bridge between the user's applications and the hardware it runs on. The kernel is responsible for deciding which memory each process can use and determining what to do when insufficient memory is available. In this case, if there was no kernel, the Chrome window may just take up all the memory and leave none for the input or output, and all you'd see is a blank screen. Talking of screens, whenever we write a program and use something like printf, it displays the message on the screen. This is also done by a kernel. When we run the program, the user mode issues a system call. This system call switches the mode bit, which is by default 1 in the user mode, to 0, which switches the mode to kernel mode. This kernel mode would then access the monitor and print the message inside the printf command. Some other functions of kernel are the implementation of virtual memory, demand paging, device management, and security. When we run an app, we don't really choose what hardware it can access and use. That is the responsibility of the kernel. So when we talk about the kernel, it's a part of the operating system. It's also just a program in the computer. In some operating systems like Linux, we can change the kernel if we want. But kernels usually have this sort of basic structure where there is an outer layer of OS and then there is an inner layer of user space and then there is an even deeper layer of the kernel space. Now here we have two major kinds of kernels among other types, them being monolithic kernels and microkernels. These kernels work slightly different to each other. The monolithic kernel, as the name suggests, stores the kernel and the user mode in the same address space. This makes the system faster as the OS doesn't need to spend more time going back and forth as much. But the drawback of this sort of monolithic approach is that if and when a component of the kernel like memory allocation or device management goes wrong, the entire OS crashes, which is not ideal. This sort of crash is what happens when there is a blue screen of death on Windows or kernel panic in Linux. The kernel just doesn't know what to do next, so it just crashes the entire OS. Modern monolithic kernels such as Linux kernel, the FreeBSD kernel, and the Solaris kernel, all of which fall into the category of Unix-like operating systems, support loadable kernel modules, allowing modules to be loaded into the kernel at runtime, permitting easy extension of the kernel's capabilities as required, while helping to minimize the amount of code running in kernel space. Meanwhile, in microkernels, we see that the user space and the kernel space are separate. This means that only the very important parts of a system like memory management are in the kernel and rest of the processes are in the user mode, which allows the kernel to be more modular in a way. This means when the kernel has an error, the entire OS doesn't just crash because the user side of the OS is still fine, only the kernel side is malfunctioning. Hybrid kernels are a hybrid of both monolithic and microkernels. These kernels are similar to microkernels, except they include some additional code in the kernel space to increase performance. These kernels represent a compromise that was implemented by some developers to accommodate the major advantages of both monolithic and microkernels. These types of kernels are extensions of microkernels with some properties of monolithic kernels, which is the best for speed and reliability. There are a few more lesser known kernel types like nanokernel, the exokernel, and the multi-kernel.